Okay, so we're going to look at calculus in this video, move on a little bit further from where we went to in the last video, and more specifically I suppose we're going to look at differentiation. So differentiation is a particular concept that we have in calculus, and it's to do with or related to finding the slope, which is where we kind of left off in the previous video. So we can start from where we have here. I suppose we can use calculus to quickly find the slope of any curve, and we're noting again that the slope generally depends on x. That's what we saw in our previous lines, and we can think the same kind of idea for our curves, our quadratics, our cubics. All of those curves that we've seen generally have an x and a y value, with the y value usually being dependent on the x value. And our rule here is that if y is equal to x to the power of n, then dy dx is equal to nx n minus 1, or the power of n minus 1. And if we were to summarize this for ourselves, our rule is that we multiply by the power and then reduce the power by 1. Okay, so we're multiplying by the power and then reduce the power by 1. So this is what we can see happening here. This n that was up as our power in the next step is multiplied at the front, and the n itself that was the power has now been reduced by 1, so 1 has been taken away from it. And this process is called differentiation. So if you're asked to differentiate, this is what you're being asked to do, to apply this rule. And dy dx is called the derivative, and often it's called the first derivative, to be more specific about it. It's often called the first derivative. So dy dx, the derivative, we've seen it called the slope, or we've kind of considered it the slope, we've considered it rate of change, all of these words that we've kind of heard before. Okay, so we're tying all these words together, we're getting used to kind of working with them all and how they interact with each other. So looking at some examples, we're going to try and find our dy dx. So if we have y is equal to x squared, we're going to apply our rule. So dy dx is equal to, first of all, we multiply by the power. So my 2 that's up at the top here, multiply by that first. So now we have 2x. We had previously a 2 up here, and that 2 now is going to be reduced by 1. So we're reducing that by 1. So my overall answer will be 2x, or x to the power of 1, or we can just say x. Either way is still correct, it's completely fine. For my second example, dy dx is equal to, same thing again, we multiply by the power first. So we have a 2 already at the front, we're going to multiply that by 3. Okay, this dot here means multiply, but we can make it a bit clearer maybe with a multiplication symbol. My x to the power of 3 is going to be reduced by 1. So again, my overall answer becomes 6x squared. Looking at the final one here, where y is equal to 4x, or 4x to the power of 1. We multiply by the power, we get 4. We reduce the power by 1, we get x to the power of 0. What we need to remember here is from our rules of indices, anything to the power of 0 becomes 1. So our answer is just 4. Okay, so that is coming from our rules of indices. So let's just make note of that. Rules of indices. And if you're unsure or you forget that, those are in your formula and tables book. So maybe have a look back over those rules of indices as well. So just summarizing what we've kind of looked at there, our dy dx is called our first derivative. So we said derivative, now we're maybe being a little more explicit about it and saying first derivative. Okay, so dy dx is the first derivative, and we may also see it written as this here, f dash x, or sometimes f prime x. It's f with the little apostrophe there before the x symbol. And where we'd see this most is if your equation, or if your graph, or your formula, or your function is given as f of x, if it's given as a function. If you're given f of x, you generally will write the derivative as f dash x, or f prime x, instead of dy dx. So if we even kind of consider the previous ones, generally if we have a y here, we'll see dy dx here. What we're going to get used to then is if we have a function, a question where maybe we have, say, f of x is equal to 4x squared, we would expect to find f dash x or f prime x, which would be 8x in that case. So we can see that kind of the form that our question is given in determines the form or the name or the label that we're going to give our derivative, our first derivative. And even just being more explicit down here, we're saying that this is differentiating with respect to x. And that comes back to our rate of change. We said the rate of change of y with respect to x. So saying that we're differentiating with respect to x just means that the variable we're differentiating is x. The variable that we're applying our rule to is x. And again, the process is called differentiation. Our rule that we had there was multiply by the power of x, reduce the power by 1. This here is just a summary, I suppose, of what those interactions look like. So the first one we saw with our last example there, if we had a question where it's just a number and then an x to the power of 1, your derivative will just be that constant, that number. If it's x to the power of n, we see more closely to what we had originally when we defined our rule. Number 3 there just kind of talks about if there's a number in front of your x to the power of something, then that has to be included in that multiplication at the start. We saw that in the previous examples as well. We saw that in example 2. The last one is one that's really worth taking note of. And what it means is if we have a constant, if y is equal to a constant, then our dy dx is equal to 0. And we can maybe think about this one a little bit. So if y was equal to 4, that would mean that dy dx is equal to 0. And if we want to just be quite strict about this in terms of the rule, if y is equal to 4, we can see there is no x value there. So you could think about it, if you liked, as x to the power of 0. So you multiply by the coefficient of x, you get 0, so your answer is 0. If we want to think about it in terms of slope, if we have y is equal to 4, so we can draw maybe a quick sketch here, not too accurate, but it'll do for what we're looking at. If y is equal to 4, that's along this line here. This is the line y is equal to 4. And we can see that this line, no matter what x is, y is equal to 4. If x is equal to 1, y is equal to 4. If x is equal to 4, y is also equal to 4. So the rate of change of y is 0. Y isn't changing. It has no change, it has no rate of change. And even more than that, it's not dependent on x. So it can't have a rate of change with respect to x, because it doesn't depend on x at all. So that's kind of the idea with that one, but it's one that's worth getting into your head, just to know that if we have y is equal to a constant, then dy dx is equal to 0. Your derivative is equal to 0. Okay, we have a few more examples of finding the derivative. I'm going to skip over the first two and I want to look at the third one. And all that we need to note here with this third one is that because we're given the question in the form f of x, we are now going to write our answer as f dash x, that new notation that we saw now, f dash x. And the rule that we apply is exactly the same. So the 3 is going to be multiplied by the 2, which was the power up here, and our x goes from 2 to being a 1. So we reduce the power by 1. So our answer is going to be 6x, or x to the power of 1. For the last example here, the difference that we have this time is instead of having dy dx, we actually have ds dt. And this comes from, I suppose, our variables that we have here. So we can think of, in place of where y usually was, we now have an s. In place of where x usually was, we have a t. So we're used to having the rate of change of y with respect to x, but this time it's the rate of change of s with respect to t. And again, we can apply it the same way, and our answer actually just ends up being t. Okay, so our 1t to the power of 1. Okay, let's push on a little bit further. We only have a little bit more to do. So if we have an expression with more than one term, we differentiate each term separately. if we're finding dy dx, if y is equal to 2x squared plus 3x, to find dy dx, we just go through each term on its own. So let's look at 2x squared first. To find dy dx of 2x squared becomes 4x. If we look then at 3x to the power of 1, that's going to become just 3. Okay, so our answer is 4x plus 3. Okay, and just comparing those two parts. So we just do each of them separately, but keeping them together. So I suppose when I'm saying separately, we mean that we're applying the rules separately, but the actual answer is all still one equation. We can apply the same thing for the next one. dy dx is equal to, first of all, let's do this 6x cubed. If we differentiate that, we get 18x squared. Next, let's look at the minus half x squared. That becomes minus x. And lastly, if we look at the plus 2, we have to remember our new rule that we saw. 2 is what we call a constant. It has no x value. And we've said that if we differentiate a constant, the answer is 0. So we can say that that's 0, or we could leave it out altogether and write our answer as 18x squared minus x. Okay, so the same thing, we're applying the rule the same way, we're following things along, just making sure to do each one at a time, applying the rule to each term individually. So the last part we need to look at is how to find the derivative at a particular point. So to find the value at a certain point, we're going to differentiate, and then we're going to sub in that value of x. Okay, this comes back to what we were looking at when we were talking about the curve, and I'd said that calculus was going to let us find a general expression for the slope, and we could use that to find the slope at particular points along our curve. So if we look at this first example, dy dx is going to be 6x minus 2, applying the same rule that we had in the previous section, and we're asked to find dy dx at x is equal to minus 2. So let's do that. We can write it the same way we would write it with fractions if we like. And we're subbing in minus 2 anywhere that we see x. And for this question, there's only one point. Becomes minus 12 minus 2, which is minus 14. And that means for us that for this particular function, if we were to graph it at the point x is equal to minus 2, the slope is minus 14. Looking at one more example, we're told if f of x is equal to 4x squared minus 3x plus 2, we're asked to find f dash of 1. So we need to first of all make sure that we're clear about what this means. So we know that f dash x is the derivative of f of x. And what they've also told us, the second piece of information they've given us, is that they want us to find it when x is equal to 1. So first of all, let's find f dash x. Applying the same rule again, we get 8x minus 3. We've been asked to find f dash of 1. So let's just sub in 1 again anywhere that we see x. We get 8 minus 3, and that is equal to then 5. Okay, so these are the important types of questions, I suppose, to be aware of and just to be comfortable with. All of this, I suppose, if we're summarizing again, comes back to these key points that we had written up here. So this idea that dy dx or f dash x is the first derivative, we are differentiating with respect to x, and to find the derivative we follow this main rule here in the center. So this main rule here, multiply by the power, reduce the power by 1, not forgetting this extra step here. If we have a constant, the derivative is equal to 0. If we can keep all of these straight in our head, then we'll be able to follow through with a lot of these questions fairly easily.